recover some ground that we did last week and go over that chi-square, some of the chi-square calculations that you might likely come across on the test this week. I'll be posting a homework tonight that includes a problem that involves one of the methods for t-tests, one of the methods, a simple chi-square example, and a very simple basic analysis of variance sample. I'm also going to show you another quick video that I put together that'll kind of put analysis of variance into perspective for you, I hope. So we're going to play around with this right now and see what we're going to make of this stuff. And as we go forward, I think that you guys will be able to pick a lot of this up. Yes, I will be uploading it to Blackboard. I'm recording now. I've had some issues with the recordings, as you guys know, so I've been trying to cut them down, make them a little briefer, and so on and so forth. I'll be posting a link for tomorrow night also, and a link for either Saturday or Sunday during the day sometime to have a session to review issues for Blackboard. Tomorrow night's session, I'll cover the interim exam, so you can go. So we'll have an excuse to go over single sample t-tests and confidence intervals. And I'll also kind of incorporate the other kinds of t-tests that we might run into also. On Saturday, maybe we'll reserve that for Saturday or Sunday. Maybe we'll reserve that for chi-square and analysis of variance, so we get another look at that. Maybe even go over that homework assignment as well. The interim exam, I'm just finishing up. I still have, some of you guys have grades. I know you have grades for it already, and a few of you know you don't have grades for it, but I'll finish those up as well. And tomorrow night, I'll actually go over question by question the answers to all of those and why the answers are like that. Okay, so you'll be able to get a look at why you got something wrong. Okay, so I'm going to get started. So let's talk about chi-square. Chi-square is an analysis that you use when you're working with categorical variables, nominal variables, in other words, names. Perhaps you want to show that there's an association between smoking in a certain population and aortic stenosis. Aortic stenosis is hardening of the arteries or clogging of the arteries of the aorta specifically. So we're interested in knowing if there's an association that's involved there. Now, you might survey a number of people. I'm going to open up a data file. Okay, you may not have this easily accessible to you. I believe that there's an SPSS version of this that's uploaded. It may be there or may not be, but you can look over my shoulder as I do this. Now, let's presume that we sampled people that we took a population of people that were experiencing aortic stenosis, and maybe we matched them with people that were same age range and so on and so forth, but weren't experiencing aortic stenosis. And we found that within those groups of people, we had 97 people who were smokers, and we had 121 people that were non-smokers. And then we analyzed we tested them for aortic stenosis, and we found that 54 in one group and 44 in the other group had aortic stenosis. So now we want to decide, is there an association between smoking and aortic stenosis? So what kind of variables do we have here? We have two categorical variables. We have smoking status, yes or no, that's one categorical variable, and we have aortic stenosis. That's another categorical variable. You have it or you don't have it. This could be any number of things. This could have been, maybe we're curious about whether people with different hair color smoke or not, right? So we might have had in the rows for our exposure, we might have had blonde, brunette, redhead, so on and so forth. Maybe just those three. And then in the outcome on top here, we went ahead, yes, they're a smoker, no, they're not a smoker. Interesting thing there is that that's three values, blonde, brunette, redhead, versus two values. We have a 3x2 table instead of a 2x2 table. You could have either, right? You could certainly have a 3x2 table. You could have a 5x7 table if you wanted to. If you had more values for the categorical variable, for at least one of the categorical variables. For instance, ethnicity might give you might want to compare whether or not different ethnicities are more likely to be smokers or non-smokers. So your columns might be smoker, non-smoker, and then you might have 6 or 7 or 8 rows for different ethnicities. And you might test the risk for being a smoker for each ethnicity, and you might want to compare, you might want to examine whether or not there appears to be a difference in the rate of smoking between different ethnicities. And this is a way that we're going to do it. We're going to work with a 2 by 2 table because it's the simplest form of this. It's going to be easiest to learn, right? So here are the values that we actually measured. Anybody know what we call those values? In the textbook and the lecture and so on and so forth, what do we refer to those values that we actually measured? Right? Yeah, observed values, right? These are our observed values. I'm going to duplicate this table, okay? Except this time, I'm going to paste it down here. Except this time, I'm going to take out these numbers, right? There's still going to be 97 smokers and 121 non-smokers, right? And we're still going to have 98 people have stenosis, 117 that don't. But I'm going to say to myself, what would this table look like if there was no association between being a smoker in this group, in this population, in this group, and not being a smoker? Well, first thing I'm going to do is I'm going to say, how many people are here altogether? There, in total, we're talking about, in our sample, 218 people. Out of those 218 people, a total of 98 of them have aortic stenosis. So the prevalence or the risk of having aortic stenosis for the entire group is equal to 98 divided by 218. That's our prevalence, a little under 50% for this high risk group that we're talking about. Okay, so now I say to myself, okay, well, when I say there's no association, this is my expected values if there's no association. If I say there's no association, then it doesn't matter if you're a smoker or a non-smoker. You should have it at the same rate, 45%, right? 44, 45%. So I'm going to fill in each one of these boxes with that assumption. There's 97 people that were not smokers. So I would expect that out of those 97, 45% of them are going to have aortic stenosis. So I would expect to see 43.6 in there. Okay, notice now with expected values, we don't always get round numbers, right? Like we do here. Here we have to get round numbers because there are actual people in each one of those boxes, representing each one of those boxes. So how about for people that are non-smokers, right? Well, I would expect the same rate. So for the 121 people that are non-smokers that we examined, I would expect them to have aortic stenosis at the same rate as the smokers. And if we add these together, trust me, it's going to come out to be 98. Okay, so here is going to be the difference. It's going to be equal to 97 minus this number. Oops. Click in there. Good. There we go. And this is going to be equal to 121 minus this number. Oops. Hang on a second. Minus this number. Okay, got a soft finger today. It's not pushing the keys down hard enough. Okay, and this will add up. You can see that this adds up to the same number also. So this is what we expect our table to look like. I can see right away that I get more, looks like I'm actually have more people that among the smokers, I'm getting more people than I would have expected that have aortic stenosis. And under the non-smokers, right, I'm also getting more, but it's a bigger population, so it's hard for me to tell what's happening here, right? Well, I'm getting fewer than I would have expected. So we're getting more smokers. We're getting fewer, more smokers having aortic stenosis than we would have expected, 54 instead of 43. And we're getting fewer non-smokers having aortic stenosis, 44 out of 54 out of 121. So we're getting fewer that. So we see differences here. Now, the thing is that if this is my expected rate, and I did a survey like this, I randomly selected people from this at-risk population, I wouldn't expect to get exactly the same numbers as my expected values. In fact, I can't get the same numbers because they're fractional. Yes, I can see a hand up there.
So I was just wondering, when you calculated the prevalence, how do you know like, how do you determine which like column to use?
Okay, well, the prevalence, I'm looking for the rate in the entire population. So the entire population is 218 people. And how many?
I understand how you got the prevalence. I'm seeing like when you were getting the 43.6 and the 54.3.
Okay, what I did there was I said to myself, I have 97 people that are non-smokers, that are smokers, excuse me. So I would expect them to be getting, if there's no association between smoking and aortic stenosis, I'd expect those 97 people, 45% of them to have stenosis, because that's the rate for the entire population.
And the reason why you're doing that as opposed to like the people with stenosis and not is because that's like smoking is
my exposure. Right, smoking is my exposure.
Isn't changing, the smoking is what's causing the
right. That no, the smoking is what we're proposing causes it. Right. Now you could argue, it's going to be a silly argument here. You could argue that aortic stenosis causes smoking. Right. I mean, you could reverse these columns and rows. Obviously, that doesn't make any sense.
Yeah.
But there's going to be times when it's going to be, there's going to be variables like categorical variables where you're going to say, so which came first, the chicken or the egg? Which one of these? It looks like there's an association. Which one is causative? Which one's the independent variable? Which one's the dependent variable? We're going to talk about that more when we get to regression and stuff. So yeah, there's sometimes that may be not that clear. In this case, it's pretty clear, right? If we were talking about asbestos, we'd put asbestos exposure in the rows and lung cancer or mesothelioma in the columns, because clearly one's the exposure and the other's the outcome. Okay, so now we want to know, are these different? Okay, well, there's a number of ways that we can do this, right? One way is we can say to ourselves, let's see how much different this group, these numbers are from these numbers. Like, in other words, for instance, in the observed values, I expected to see in that box, I expected to see 43, but I got 54. So how different is that? So that's equal to, the difference is equal to 54 minus 43.6. That's the difference. How about the next box? Difference there is equal to 44 minus 54. The difference in the next box is we expected it to be 53. Our observed values are 40 minus our expected values of 53. We'd expect that number there. And finally, in the last box, we observed 77. We expected that we should have gotten 66. So now these are all the differences. Anytime you actually do this, there's always going to be a difference. It's never going to be 0, 0, 0, 0. Why not? Well, first of all, it can't be 0, 0, 0, because when we're working with real people, there's whole numbers in there, not fractions, right? That's one reason. The other reason is because if I redid this sample with another 218 people from the same population and put them into these boxes, I wouldn't get exactly the same result for the observed values, right? If I did this again with another 218 people randomly selected from the same population, I wouldn't get exactly 54 among 54 people who had aortic stenosis and were smokers. I might get 52, I might get 57. So now the question becomes, how different is different enough to say that that difference is not just due to chance from sampling, but actually due to a difference in a risk due to smoking increasing the risk of having aortic stenosis. How much is a big enough difference? Well, a big enough difference is a difference that's so big that less than 5% of the time that I'll be wrong if I reject my null hypothesis that there's no association, right? There's no difference, and say that there is a difference. I reject my null, right? In other words, 95% certainty or 5% chance, less than 5% chance of being wrong. So now we're going to invent a statistic to do this with. The first thing I did was, let's add all these numbers together and see what happens, right? We did this before. If I add all these numbers together, that's not going to work for us, right? It's going to add up to 0. Oops, that shouldn't have happened. What happened there? I'm not sure exactly what had happened. It should have been 0. I must have done something wrong on one of these. Anybody know which one I did wrong? That looks right. This looks right. This one doesn't look right, does it? That one's off. Okay, and what was that? That was D3, which is 40, minus D11. That should have been D11. There we go. Oops, I kidded again. D3 minus D. What did I just? Oh no, D3 minus. Yeah, that was right. D3 minus 310. Yeah, something wrong with the observed. There should be. What did I do here? Well, maybe I made a mistake here in calculating this. That's F10. F10. Oops. That should be E10. That is E10 minus D minus C10. I still have a problem here. Let me see. Totally 94 for smokers. Oh, you're right. I know what happened here. No, somebody just pointed out I got the wrong total. There we go. 215. Okay, there we go. So now if I do the sum here, it comes up to 0. Right, see the total going across was wrong? Right, 54 and 40. The minute I saw it didn't come up to 0, I knew something was wrong there. Okay, so the total now is, if I add all these differences together, the total is 0. There's a couple of ways. I want to use the magnitude of these differences to predict whether I can reject the null hypothesis. I want the sum of these numbers to be big, right? Because that would mean there's a lot of difference between the observed values and the expected values. So I want that to be big. Obviously, I can't just use the numbers, because if I use the numbers, they'll cancel out and be 0. So I could use the positive value of the numbers. However, in a lot of cases, what we do in statistics is we'll take those numbers, in order to eliminate the negative numbers, we'll square those numbers. So I'm going to do that right here. Okay, I'm going to go over this. I'm going to take each one of these numbers and square it. And I'm just going to copy the formula across and down. Okay, and I've squared each one of those numbers now. Now I'm going to add them together. Now at this stage, I'm going to say to myself, I'm going to add them together. The only thing is, when I add them together now, I'm going to get a very large number, much larger than the real differences between these two groups. So I'm going to bring them back into the range of the numbers that I'm actually looking at. And I'm going to do that by taking each one of these numbers and dividing by the expected values, the values that I have here in the expected column. So I'll divide that number by that, and I'll divide this number by its expected value, and I'll divide this number by its expected value, and I'll divide this number by its expected value. Okay, so now I have 4 numbers that represent the magnitude of the difference between each one of these cells. Okay, so I'm going to add those all together. That value is our chi-square value. That's our statistic. The bigger the difference between the two groups, the bigger the difference, the more likely it is that there's a real difference between people who aortic stenosis and people who smoke and people who don't smoke. The bigger this, if this number is small, it's small because the differences between the observed values and expected values are small. If it's large, it's because the values, the difference in the observed values and the expected values were large, right? So that's what determines the size of that number. Well, now this number can actually be represented by a distribution, but that distribution is going to look different than the other distributions that we've worked with. I'm going to open, I'll see if I can't find it quickly online. I don't want to close that because I don't know if I'll be able to get back there again, ever again. Chi-square distribution. Okay, and I'll go into images. And it's going to look something like this. Let's take a look at that distribution. Now, what's going to happen is that it's never going to be below zero because we're dealing only with positive numbers here. So the probability, this curve represents the probability of getting this big a difference if you, for chi-square, for that value, the differences between the four cells, probability of giving that big a difference if there's no association between smoking and aortic stenosis. Look at this, pretty funny. It's very unlikely we're going to get zero. In fact, it's more likely that we're going to get a small number that's not zero than it is that we're going to get zero. So the probability actually goes up of getting a certain size number, not getting something other than exactly zero. But then once we get past a certain point, the probability starts going down. The probability of getting a number that's higher than 8 is the area that's left in this tail. So we could go all the way out here and say that we're not going to reject the null hypothesis unless we get a value of 30, which would be on another page. It would be on another screen, right? But that would be so difficult to prove. You'd have to have such a large sample size to be able to reject the null hypothesis. It wouldn't be practical, right? This is really asymptotic. It never really reaches zero, right? So we set a limit on how likely, what level of uncertainty that we are willing to accept. Well, we're willing to accept 5% chance of being wrong. Well, so we're going to go over here. We're going to get a chi-square value that leaves 5% chance of getting this outcome if there's no difference between smokers and non-smokers. So we're looking for a chi-square value that leaves 5% of this curve. Now, this particular one, these numbers look a lot bigger than the one we're dealing with right now. We got 8, right? So 8's all the way over here. Maybe 10% is left over or something like that. There's a different distribution for each situation where you have a certain number of columns and rows, degrees of freedom, it's called. So in this case, this is for a table that might represent 3 or 4 degrees of freedom. So these numbers are pretty big. Our particular situation is we have only 2 rows and 2 columns, and that happens to be 1 degree of freedom. How do we get to that? We say the rows minus 1 times the columns minus 1. 2 rows minus 1 is 1. 2 columns minus 1 is 1. 1 times 1 is 1. That's 1 degree of freedom. So we want to use a distribution where the numbers represent what the outcomes we would expect for a 2 by 2 table or 1 degree of freedom. And I'm going to see if I can't find that on here. I would go back to Blackboard, but I don't want to mess around with Blackboard and trying to, going back and forth on it and then wind up getting shut out anyway. Okay, chi-square table. Okay, we'll see if we can't find one for the number of degrees of freedom that we want. Oops. Critical values. Here we go. This is a good one. Okay, let's take a look at this one. Okay, so for 1 degree of freedom, what value do we need for chi-square to be only 5% left in that upper tail? 3.841. So if I get a chi-square value bigger for a 2 by 2 table, bigger than 3.841, I know that there's a smaller area than 5% left in that upper tail. There's less than 5% chance I would get that big a number if there's no association between smoking and aortic stenosis in this analysis. So I need chi-square to be bigger than that number to reject the null hypothesis. What do we call that value? Critical value, right? That's the number we're going to need to reject it, right? So we don't calculate a p-value if we're doing this by hand. We just check the table for the critical value and decide whether that's big enough to reject the null hypothesis. When we use SPSS, we'll actually get a p-value. Give us for a specific number, like in our case, 8. Give us a specific number that the probability of getting something that big might be 1%, which is the chance of being wrong. So you would reject your null hypothesis because less than 5% chance of being wrong. But it'll actually give us a p-value or significance, right? So in this case, what was our value that we calculated for chi-square? Yeah, and what we say our critical value was? 3.84. So we would, in this case, reject the null hypothesis. We would say we reject the null hypothesis that there's no association between smoking and aortic stenosis, and accept the alternative that there is an association. Everybody comfortable with that? It's really pretty simple math. Things get a little bit more complicated. There's a few other ways to, there's a Fisher's exact test, which you saw there. There's a continuity correction. SPSS will calculate all those for you automatically. For our purposes, we're going to take a simple view of this. We're going to use this formula for chi-square. There's a lot of the reasons for using the others to be more precise and so on and so forth, particularly with a 2x2 table and certain sample sizes and so on and so forth. But for our purposes, this is the value we're going to use. SPSS will give us the other values, though. Okay, but as far as calculating with Excel, we're going to use this as kind of our baseline. Okay, so if I gave you a 2x2 table, would you be able to produce the expected values? Yes? Yeah, not so hard, right? Yes, back there. That's the prevalence. Oh, you mean not? It's actually 94. I made a mistake. Yeah, I added them up wrong. Right, it's 54 and 40. It was really turned out to be 94. I had to correct that. Yeah, I know what you're saying. But you could have done it that way, where you figured out the prevalence of smokers for each group. Like in other words, out of the 98 people that have aortic stenosis, what percentage of them should be smokers if there's no difference between? You could do it that way. You could turn it around on its side. Well, I like doing if you lay it out so that the exposure is in the rows, and the disease is in the columns, or the outcome is in the columns. You can always just say to yourself, well, I'm gonna base it on the prevalence of disease in this population, which you can see is 98 over 215, right? So I would stick with it that way. That's one of the reasons I like encouraging you to put it in rows and columns like that, so that you don't get mixed up that way. You could have had the stenosis in the rows and the outcome in the columns, and the chi-square would come out. The smoking in the columns, the chi-square would come out to be the same number, right? But the next step we're going to take is not going to work out so well. Okay, so now remember we talked about risk and odds ratios, risk and odds. Okay, when we talk about risk is kind of a little easier concept to understand when you look at this table, right? I'm going to focus on the observed values. Okay, I'm going to focus on these observed values. Okay, when we talk about risk now, okay, the risk of having aortic stenosis if you're a smoker, well, how would I express that? How about the percentage of people that have aortic stenosis that are smokers? I'm going to say my risk. If I'm a smoker, my risk of having aortic stenosis is 54 over 94. I'm sorry about getting that number wrong. So if you notice, if you get a chance, change that on your spreadsheet also. So the risk of having aortic stenosis if you're a smoker is 57%, right? What's the risk if you're not a smoker? Well, 44 out of 121 non-smokers have aortic stenosis. Which group has the bigger risk? The people that smoke, right? 57% of them versus 36%. Well, I'm gonna create a new statistic called relative risk. Another way of saying that is risk ratio. So anytime you say ratio, it usually means you're dividing one number by another. So the risk ratio is going to be a comparison of the risk for smokers versus the risk for non-smokers. And it could just as easily be the risk for people exposed to asbestos versus the risk for non-exposed. So the risk ratio is going to be equal to the risk for smokers divided by the risk for non-smokers. And not surprisingly, it's just the ratio of those two numbers. So you're 1.58 times as likely to have aortic stenosis if you're a smoker versus if you're not a smoker. And you see these risks exposed. You see these things described in the literature all the time. If you're exposed to asbestos, your risk of lung cancer is 7 times what it is for someone that's not exposed. If you're a smoker and you're exposed to asbestos, it's 35. You hear these risk ratios expressed very often. When it's expressed in layman's terms, very frequently they use this idea of risk ratio. They say your risk is increased this much. In statistics, we tend to use a different kind of measure. It's almost the same thing. There's a few reasons why we do it. For our purposes right now, it's not important why. We use, instead of risk, we use odds. Okay, and the way the odds are calculated is a little bit different. The odds is basically the number of outcomes that involve stenosis, that's 54 in this case, over the number of people, put an equal sign there. The odds are the number of people that have stenosis, 54 for smokers, over the number for smokers that don't have stenosis. So instead of 54 over 94, it's 54 over 40. People that have it versus people that don't have it within that row, right? So the odds are yeah, okay. What about the odds for not having for non-smokers? The odds for non-smokers are 44 over 77. Good. Okay. So now, again, this time I'm going to calculate something called an odds ratio. And how do I calculate that odds ratio? Same way I did before. I'm going to say it's equal to the odds for smokers over the odds for non-smokers. I got a different number, 2.3, right? It's a slightly different measure. Very frequently, like when the prevalence is not that high, they'll be pretty close to one another, right? But it's kind of a slightly different measure, but you can see it's basically a very similar kind of measure. Well, now, yeah, they tend to be pretty close to one another. In this case, because it's such a wacky, made up distribution, they came out a bit different. However, the important thing is not so much what that number is. The important thing is if there's no association between smoking and stenosis, what would you expect the risk ratio to be? The same. You'd expect the risk for smokers to be the same as the risk for non-smokers. So if you got two numbers, one over the other, and they're both the same number, what do you get? You get 1. You would expect this to be 1. That's what we would expect it to be. What about the odds ratio? What would you expect that to be if there's no association? Same deal. You'd expect that to be 1 also. You'd expect the same ratio between yeses and nos in both of these rows, right? So now. So instead of using chi-square, we can look at this idea of risk and odds, and we can say to ourselves, "Oh, it appears that the risk ratio, the relative risk or risk ratio, is greater than 1, or is different than 1. In this case, greater than for." Smoking versus non-smokers, and the odds ratio is different than 1. The question now becomes: is 1.57? Is that different because it's just chance, or is it different enough that I can say that that's a real difference, statistical difference, with less than 5% chance of being wrong, with a 95% confidence that it's different than 1? Okay, and how about this 2.35? Can I say that it's different than 1 with a 95% confidence that it's really different than 1? The number is not quite as important as whether or not it's really different than 1. So I got a number that I'm comparing to another number where I really don't know whether that number is precisely right, that 1.57 or the 2.3, but I can calculate a range of numbers that I can say that I'm 95% sure that the value is between those two, right? This is kind of a binomial distribution, isn't it? Yeses and nos here. It's stenosis, no stenosis. So what we're really interested in is whether or not the 95% confidence interval for 1.579 and the 95% confidence interval for the odds ratio excludes 1. It's different than 1, doesn't have 1 in it. In that case, what can we say? We can say it's different than 1, which is the same thing as saying that there's a difference in risk for smokers and non-smokers. There's different in the odds for smokers and non-smokers. Yes?
So I think you might have said it, but so are these different by chance or because there is an association? So if you're saying that it is by chance, then you're just saying that there's no association that you're
exactly.
that you're
Yeah, exactly.
even on the top.
In other words, it wouldn't be very unusual for me to get a risk ratio of 1.1, right? That doesn't seem like, because I'm never going to get exactly one because the two groups I'm taking these random sample of people, so the likelihood I get exactly the right ratios in each one of these two rows, it's kind of unlikely, right? It's like kind of flipping a coin 100 times and expecting to get exactly 50 heads. It's kind of like that. And these guys online, they're doing a great job online because they're answering their own questions. This is terrific. Square difference, back on the spreadsheet, rejecting no hypothesis. Okay, good. I'm glad you guys are working on that right there. Okay, so I'm not going to be expecting you to calculate at this stage, when you take another statistics course, you can really get into this, and figure out how to use this idea of these binomial outcome to figure out what the confidence interval is and so on and so forth. Although you could do it if you wanted to based on what you know already about binomials and how you calculate standard errors for them and so on, standard deviation, standard errors for them and so on. You could do it if you wanted. I'm not expecting you to do it by hand. We'll see about using SPSS to do it instead. Okay, so now this is really it. This is all. We've calculated odds ratio, relative risk, we calculated chi-square. We actually we went to a table, looked up whether we could reject the null hypothesis. This is really the basis of using chi-square, comparing categorical variables and being able to determine whether there's an association or not. If you want to work on your project and you want to say, is there a difference? Is there an association between eating a lot of fruits and vegetables and living in a high income neighborhood or low income neighborhood, right? High or low, a lot of fruit, not a lot of fruit. You could actually manipulate those categories. So like maybe you can narrow it to 2 categories instead of 18 or something like that. But maybe that you might want to look at those two. If you're looking at categorical variables, this is the kind of analysis that you're going to want to do. If you're looking at numerical variables, what's the BMI for people living in Brooklyn versus people living in Queens, right? That's a numerical variable. You'd use a t-test. And we're going to talk about very briefly, if you're looking at the BMI for Brooklyn, Queens, Manhattan, Bronx, and Staten Island, 5 different groups. It's still a categorical variable. Borough is a categorical variable. You're in one of those 5 boroughs, right? Okay, but the BMI is a numerical. If you're looking for the average for each of those 5 groups, then you wouldn't use t-test because you got more than 2 to compare. You would use analysis of variance. We'll talk about that in a second. Okay, so let's now go to SPSS. I have this same data saved in an SPSS file. I think I have SPSS open in the background, do I? I was hoping I did. Oh no, it's going to bounce around for a while. I'm going to do this same analysis using SPSS, if it ever opens. Okay, you guys online have any questions while we're waiting for this to start up? You might also, hey guys, remind me if you ask a question to repeat it because they won't be able to hear you. You've noticed that in the lectures. And like a lot of times, if somebody asks a question, you can't really hear what you in the spreadsheet, you use Excel to calculate chi-square. Yes, in the spreadsheet, I used Excel. You could use plain calculator. You don't have to use Excel, right? It's just math, right? But yes, I'll record tomorrow night session. And in fact, I'll have a couple of ways to record it at home so that it works a little bit better. Most likely like 9 o'clock. I'll put a link up. They're on there now. If you look in session 11, the PowerPoints are there. Can you see them there? There should be like the second item down or something like that, just underneath the. Oh, are you looking at the announcements or the class session? Session 11? I thought that was there. Let me, while we're doing this, let me just open that up. Oh. You guys online can see the issue we're having with Blackboard. It's not coming up. Let me try it this way. If I do it this way, I might be able to get on. Yep, that way. If you go to the portal, it'll let you on. Okay, well, it opened in the background, by the way. Okay. And you guys know, when I can, I record every one of these things. It's just occasionally there are technical glitches. That this is, we're going to be doing a completely online course in the fall, which should be a very interesting experience, given the amount of time that we have issues with, getting on Blackboard and internet connections here and so on and so forth. Class sessions. Okay, so here's our session this week. And yeah, it should be available. PowerPoint should be session 11, right? These are the links. Yeah, and there's a PowerPoint presentation thing. Okay, it's there. Let me just make sure these other things are available too. Here's the stenosis, the SPSS file. Here's the chi-square version of that same file, the one I was just using. Okay, so let me go back here. And okay, I know that. Okay. By the way, apparently I checked with ISIT, and it'll let you use it for 30 days past the expiration date, which I think for me is going to be just after the class is over. So I'm just going to squeak by. All right, so at any rate, here is smoking, disease, and gender. These are all categorical variables. Now, you may notice that I'm in data view right now. If I go up here to view and I turn off value labels, you'd notice that these are all numbers, zeros, ones, and twos. Right? If I go into variable view, you'll see that if I click into smoking, 1 means a smoker, 2 means a non-smoker. If I click into disease, which aortic stenosis, 1 means yes, 2 means no. And gender, there it is. Gender is 0 means female, 1 means male. Okay, so I can use any of these. I can combine any of these in rows and columns, but I'm going to do the ones that seem to make sense to me. I'm going to go back to the data view. I'm going to turn on the value labels so I can see them. Okay, and I'm going to say, and this is, number 1 is a person, number 2 is a different person, number 13 is a non-smoker, non-smoking female who does not have disease, right? And so on and so forth for all of these various people, all the way down to 215 people. I think there's one more than, might be a little bit different. It looked like we had 214 before in the other file. Analyze, I'm going to go into, now we're working with crosstabs. We're going to build a table. I'm going to go into descriptive statistics, crosstabs, right? And I'm going to say in my rows, I'm going to use the exposure I'm interested in. The exposure I'm interested in is smoking. That's the exposure I think is going to cause disease. And in the columns, I'm going to put the disease. Could be lung cancer, could be whatever, it could be diabetes. In our case, it's going to be presence of aortic stenosis. So right now, there's no statistics checked off to be done. In cells, the only thing checked off is observed values. So I'm going to say continue. I'm going to say okay, and SPSS will bring up the output window. And I'm not going to, I'll do something as soon as I get done with smoking, we'll take a look at it. Okay. Smoking status, okay, 54, 40, 94. This is the same data that we were looking at before, with maybe a slight difference. What, did I get 215 before? I guess it was 215, right? This is the same table. This is our observed values. Maybe SPSS can also give me a table for expected values. So I'm going to go to Analyze, Descriptive Statistics, Crosstabs again. Whoops, not what I wanted. Analyze, Descriptive Statistics, Crosstabs. This time I'm going to go into cells. I'm going to ask it to also calculate my expected values. Then I'm going to click OK. And I'll click OK again. Okay, and this time it calculated my observed values, and for each one of these boxes, my expected values. The only difference is it didn't bother to build 2 separate tables. It put both values in each cell. 54 was the observed, 42.8 was the expected, and so on and so forth. right? So it actually calculates that. We had to figure out the prevalence, multiply it by each total by the prevalence to get the number of people with disease, and subtract from the other one. We got to do a little bit of math to do it. But SPSS now is doing this for us, right? So, okay, you observe minus expected. Oh, let me, I see we got an audio problem here. Let me just make sure everybody's muted. Okay, I think we're okay now, right? Okay, and the formula, as someone is pointing out online, the formula is observed minus expected squared. Don't forget to square it over the expected value to get each cell. So now we're going to do that calculation. I'm going to calculate chi-square. Well, for chi-square, I don't really need the observed values. So I'm going to go back to just, we don't need the expected values. It's going to calculate it for us. I don't need to see them right now. So I'm going to turn them off, because I have a reason for doing this. You don't have to turn it off if you don't want to. I'm going to ask it to calculate for me chi-square. You guys remember what we got? Got 8 point something? I think so, something like that. So now, let's see. You know, I think the numbers are, did I have 214 before? I see we got 8 point, what's that? I had 215? I'm not sure why I'm not. At Pearson's chi-square, without the continuity connection, I should get the same thing. I'm not sure exactly why I'm not getting the same. I might have slightly different numbers or something like that. Or maybe I made a mistake in calculation before. But my Pearson's chi-square, this observed minus expected squared over expected, is 9.48. Okay? Is that big enough for us to reject the null hypothesis? In this case, we're not going to go to the table to look up the critical value, which is we know is 3.84. In this case, we're just going to go across here to look at the probability of being wrong if we reject the null hypothesis, our p-value. Okay, and what's our p-value equal to? 0.002, or 0.2%. Is that lower than our acceptable level of error, which is 5%? Yes, it is. So we reject our null hypothesis. These other versions of it, the continuity correction, the Fisher's exact test, these are also calculated by SPSS, and the probabilities are calculated for them as well. We're not going to worry about them for now. We're just going to worry about our basic chi-square, Pearson's chi-square, or basic chi-square calculations. So I'm not going to ask you to do that. Okay, so now I'm going to do one more thing. See these tables here? I went back to just the observed values. Okay, I'm going to ask SPSS, analyze descriptive statistics, cross tabs. I'm going to ask SPSS, I'm going to go into cells. I'm going to ask it to give me the percentages by rows. I'm going to click continue and click OK. Now, if I look at that table, what does it show me in that table now? It shows me not only the 54 and the 40, it shows me that 57% of this group, the smokers, had aortic stenosis, and only 36%, that's our risk, right? Our risk is 57%. Our risk for non-smokers is 36%. Our risk ratio is going to be 57 over 36. Now, you would think, okay, let's get SPSS to calculate our risk ratio. And as a matter of fact, what it didn't do is give us our odds ratio, right? Because that's not, you can't just do that by rows. So I'm going to go to Analyze, Descriptive Statistics, crosstabs. I'm going to go back into the statistics, and I'm going to ask it to calculate the risk for me. Okay, and I'm going to click OK, and OK. And let's see what we wind up getting. It repeats the table for us, and it gives us our chi-square tests, but then it also gives us our risk estimates. Remember what we got for odds ratio? We got 2.36. There's our odds ratio. And what about our, what did we get for our relative risk? We got 1.58. So here's our odds ratio. Here's our relative risk. That's calculated for us. The odds is obvious because it says odds ratio. The relative risk takes a little bit more interpretation. You can see it's 1.58. This other number, cohort aortic stenosis equals no. This is the inverse of the odds ratio. In other words, the probability of not how protective, or what's the probability of not having aortic stenosis if you're not a smoker. So, but the one we want. What's that? The relative risk and risk ratio are the same thing. Okay, so what is the important thing about this 2.63 and the 1.5? Is it the absolute numbers that's important to us right now? No, we got to know if those numbers are big enough to say with 95% certainty that they're different than 1, which is what we would get if there's no association between smoking and the risk for smoking and the risk for, it's no difference between the risk for smoking and the risk for non-smokers, right? So what do we need to be able to exclude 1 as a possibility and reject our null hypothesis? We need to compare that number, 1, to our confidence interval. In other words, the value that we got for the odds ratio was 2.3. Our 95% confidence for the true value of the odds ratio for the entire population is 1.3 to 4.1. What's not between those two numbers? 1. So we can reject the null hypothesis. Had they been 0.9 to 4.1, we would have not been able to reject the null hypothesis because we couldn't say with 95% certainty that the odds were different than 1. Okay? Right, so that's the game here. Okay, and you can use SPS, and of course, you can click on these, copy, paste it into a Word document, any one of these tables. But you've seen how I went back. You could have, of course, gone in here to descriptive statistics and crosstabs, and you could have just gone in here and said, okay, calculate everything for me. Calculate the risk, go into cells, calculate, percent expected value, and so on. You could have done that all at once. I just did it step by step to make it a little clearer what was going on with SPSS. Oh, yes. That right. The significance is, the chi-square value, if you're doing it by hand, the chi-square value is important because you need it to compare it to the critical value. If you're doing it using SPSS, you're going to be going to look at the p-value, the significance, to see if it's less than 5%. It'll still give you the same number, but that's, instead of going to a table, you're going to be looking at that to see if it's different enough. Yes, that was whether or not we need the chi-square value. Yes? And the relative risk, odds ratio, relative risk doesn't come out right? Yeah, as a matter of fact, that's one of the reasons you may notice that there's 4 different ways that you can do, just in this alone, that you can do chi-square. That's going to be a rare situation. So for our purposes, you got enough on your plate to worry about. You don't have to worry about, like all these. I don't want to bog you down, especially since, this is an introductory course, and especially since we got so little time left for projects and the rest of this. I don't want to bog you down on like having to work through all these different calculations and have to worry about, well, which one is the more appropriate one in a situation. If you're a real statistician, or if you're going to go on to the next level of this, that's going to be important to you. Like, why would we use a continuity connection? When and why we use that? And when and why do we use these Fisher's exact test and so on? Right? They're all versions of chi-square, right? But the Fisher's exact test is really remember when we did the t-test with proportions? It's really kind of like doing the t-test with proportions, right? Rather than doing kind of a chi-square. But it's really the same thing, right? This is really just another version of all that. It's a way of comparing categorical data. Okay, so let's put that to bed for now. Like I said, I'm going to put up a homework with probably 3 or 4 examples. Maybe one, something you do by hand, by a calculator or Excel, and a couple other things, chi-square, analysis of variance, t-test you do by using SPSS. And then you'll have some other stuff, conceptual stuff, maybe from the PowerPoints or something like that. Like, for instance, it's worth knowing what are the assumptions you make when you use chi-square. What assumptions do you make when you use the t-test? And I guarantee you in every one of these PowerPoints, the one for t-test, the one for chi-square, the one for analysis of variance, there's at least one slide that says these are the assumptions, 1, 2, 3, 4, right? And so on and so forth. So yeah, I think those would be pretty easy, especially since the open book shouldn't be too challenging. Okay, so but you got to know where they are, so you don't have to kill a lot of time looking for them. So, oh, that's a good idea. Okay, so I'm going to stop recording here and then restart. Okay, you guys, I hope you guys are back again. Okay, guys, I hope you guys are back again. Geek, geek. Okay, so at any rate, um, okay, so you got to look at that the idea of the variability between the means of samples and the variability within the groups are related in such a way that the further apart the means are for the sample and the narrower the groups are, grouping and numbers within each group are, the more likely it is that you're going to be able to distinguish between them, be able to say that you reject the null hypothesis. And in this case, the null hypothesis is that the mean of group one, the mean of the population for group one is equal to the mean of population for group two, and the mean for group three. So that's really what we're interested in testing. Okay, and we actually can calculate this. I have data. There's another video. I'll put the links to this other video where we're running a little low on time. So I'm going to show you some data in Excel file. Let me get to it here. That's that one. I can close that one. Okay. Okay, so here is a situation where I have three groups. I happen to name the three groups by people using people's names rather than using group A or group B or group C. I just gave it people's names, but they're just three groups of numbers. They could be variables like Brooklyn, Queens, Manhattan. Could be blondes, brunettes, redheads, left-handers, right-handers, ambidextrous, and so on and so forth. There's some values within that, some numerical variable that we're measuring within each one of those groups. Okay, so we have three groups. So in this case, just with those names. So now, if I'm interested in the variability within each one of these groups, we've done this before, haven't we? For instance, we know for Fred here, we would calculate the average for the sample of 5 values that we have for that group. For the second group, we calculate the average for this group. For the third group, we calculate the average. Right? So now we have the average, the mean for each one of these three groups, the samples from each one of these three groups. So now we say to ourselves, okay, so I see what the means are. What's the variability like within each one of these groups? And what do we use for variability? We use variance and standard deviation, right? So how do we calculate that? We'd actually go in here and put 1.8 down here, and I'm going to copy it down rather than recalculate all this. And I'm going to copy that down. And I'm going to copy this down. Okay, and the mean, oops, actually, I meant to use that as, okay, so that's our means, right? X bars are all our means. Okay, so what's the difference between each value and the mean? That's going to be equal to this minus this. Right, now copy that down. Okay, and I'm going to do the same thing here. This, look familiar? Right, we did this the first week, didn't we? Right, descriptive statistics, we calculated the variance. Okay, I could have used the variance formula as well if I wanted to. Okay, and now what do I do with that? I square each one of these values because I got to get rid of the negative numbers. And I'm going to fill down. Okay, you do the same thing here. And actually, I have a video that actually does this. That I'll also post a link to, where I actually go through this demonstration a little bit more slowly and carefully. Now, I'm not going to expect you to do this to calculate analysis of variance. I just want to show you where analysis of variance comes from. Okay, so I'm going to add these up. And what are these things called when you add them up? It's called the sum of squares, right? We've learned about this already. The sums of the squares of the differences, or sums of squares if you want to abbreviate that a little bit. And it's a measure of the variability, because the more variable these numbers are from the mean, the bigger these sums of squares of the differences are. Well, we're about to come up with the variance in this. How do we get the variance again? The variance is the sum of squares, sum of the difference of squares divided by n minus 1. So we're about to do that. Okay? So let me go over here and see what I can fill in here so far. The screen is not showing for us to view. Should be showing. Can you see it now? Oh, some of you can see it, some of you can't, eh? How about now? Maybe that other video is in the way on some of your screens. Maybe you forgot to get the other video out of the way. Okay, so now the sums of the squares of the differences within each one of these groups. What was that number? That number came out to be, let's see, the degrees of freedom, sums of squares of the differences within each group. That's equal to this plus this plus this. Okay, that's the sums of the differences within each of the groups. The degrees of freedom, that's